Hi, my name's Doug Nix, and in this short screencast I want to talk to you a little bit about the two-letter designations that are sometimes used to describe electrical system, distribution system grounding. We'll be talking about grounding in a variety of ways, but in particular we'll be looking at grounding on the distribution generation side, so that would be at the generator or at the power plant, at the distribution transformer, which might be on your street or might be next to the building that you live in, and finally at the point of consumption down here in either at your home or possibly over in at your place of work. So IEC uses a combination of letters to describe the way the source and the load side of a distribution network are grounded. And this can lead to a little bit of confusion for North Americans because we are not used to using these terms. We have the same types of grounding systems, but we just don't call them out in the same way. And if you're listening to the screencast from somewhere other than North America, understand that if I say grounded, I also mean earthed. Those two terms are more or less interchangeable. So I mentioned that we have two different terms that can be that we look at in this code. So on the source side, we can call out a T, and the T means that that source of supply is directly bonded to earth ground. Or we can have an I, which might mean that that source of supply is isolated from earth. And there's an interesting little wrinkle I'll show you on the next slide where we can actually have an impedance between the center point of the distribution system and earth ground, and that's called an impedance grounded system. Still considered to be isolated, but it's a little wrinkle on that. And then on the load side, we have two letters as well. We have T, which would mean that the load side of the system was also directly earthed. And if we have an N, it means that the chassis of that load is also directly connected to earth. So we can use those letters in a variety of combinations to describe the way that we are bonding the source and the load to earth. Now there's two other letters that you need to know about, and those can be attached to the first two. You can have a -C, which means combined, and that means that the neutral and the safety earth conductor have been combined into a single wire. And you can also have an S, which means that they're separated. And that gives you a couple of additional wrinkles in how the load grounds might be connected. Okay, so let's look at how that might look from a schematic point of view. In this particular case, I'm going to look at a basic three-phase alternator output or transformer. So we have three coils, T1, T2, and T3. One end of each of those is connected to a single central point, which is why it's called a Y or a star connection. And the remaining end of each of those coils is connected to a load supply wire L1, L2, and L3. And you can see how that's done in this particular diagram. Now, we can also look at specifically how those designations might be formed. So we can have three different designations. And in those designations, we're going to look at those two letter terms that I just described. So we can have a TN, meaning that the source is directly earthed, and on the load or consumption side, the chassis is also directly earthed. We can have a TT system, where both systems have independent chassis grounding. And we can have an IT system, where we have an isolated supply and a separate earth that is bonded at the point of consumption. In three-phase systems, typically in Canada we see 575 volts from phase to phase. So you can see in the diagram here we have 575 from L1 to L2 and L2 to L3 and also L1 to L3. So as long as the loads are balanced, those phase voltages will also remain balanced. In the US, we sometimes see 460 or 480 volts for those phase-to-phase voltages, and in some cases we even have 208 volt three-phase service available as well. Everything else remains the same. How we describe the grounding remains the same. It's just different distribution voltages for different purposes. Okay, so let's look at our first iteration. This is the isolated version. So we have our three coils on the transformer, our three load leads, and this is, at its most basic, an isolated or IT system. Okay, so That means that if we were to take a measurement between the chassis of the transformer or the alternator, we would find that we would have some indeterminate voltage between that center point and ground, and each of the phases might measure phase to phase 575 volts, but we'd have some indeterminate voltage between each of the phases and chassis. And there's a lot of technical explanation for why that voltage is somewhat indeterminate. I'm not going to talk about that right now. Now, I mentioned that there's a little wrinkle that we might have where we can have an impedance connected in between the center point of the transmission system and ground. And I've just drawn in that little impedance, the little resistor with the grounding point. So if we do this, what it does is it stabilizes the voltage relative to ground. And it also provides us with some control over the fault currents in a system like that, while still giving us all the benefits of an isolated system. And I can talk about those in another screencast. Whether you have an impedance between the center point and ground or not, this is still an isolated system. Okay, so let's look at the next variation. So we have our transformer and our load leads. Now we've bonded that center point of the distribution system directly to earth. So now we have a solid connection there. We have a very stable system in terms of the voltage that will be present between the chassis of the equipment and the phase leads. Otherwise it operates exactly the same way. We have 575 volts from phase to phase. Now we can add an additional conductor into this called a neutral, and if we add that wire in, we now have the option of having loads connected not only from phase to phase but also from phase to neutral. So the neutral voltage in this case would be root 3 of the phase voltage, and that would give you a phase to neutral voltage on a 575 volt system of 377 volts. Now, one further problem here is that we don't yet have the safety ground brought out to be used for connection of the load. So let's look at what happens when we do that. Now, in this particular case, because we don't have the option of bringing out that connection directly, we're going to use a combined PEN conductor. And the PEN conductor carries both the safety grounding and also the neutral central point connection. This is a connection you often see in distribution supply systems, but you don't often see in facilities or in homes. Typically, the difference between a safety ground and the neutral is that the neutral is permitted to carry current under normal conditions, and the safety ground wire is not permitted to carry current. When you have a PEN conductor like this, you're combining those two things, so you can use it for safety ground, you can use it for neutral, and it can carry current. Okay, one more variation on a theme. We have our same distribution transformer. We have the center point solidly bonded. We have a neutral wire, and now we brought out a separate ground wire, the green PE. And so now the neutral wire can carry current from the loads. The PE wire remains current free unless we have a phase fault. So if we look at this in terms of what those two-letter designations mean, this is called a TN system because the source of supply is directly earthed, and the expectation is that the load is also directly earthed. We also have a TNC system. The dash C means now that the PE and the neutral are combined. That's what the dash C means. Okay, one more variation. So this final connection system is also often used by distribution companies in supplying loads. This system is called a TT. So we have the supply side of the system bonded firmly to earth. You can see the connection from the start point to ground. The chassis of the transformer or the alternator is also bonded to that point, and the neutral, if there is one, is connected to that same central start point. And it goes out to the load. The difference is that at the load side, we do not bond the neutral to earth at all, but we do bond the local chassis or provide a local ground. So one of the issues with a system like this is that you can get significant voltages appearing between the neutral point and chassis ground. And in most homes and at the point of use in factories and so on, you're not normally expecting to see any voltage between neutral and ground, or at least not very much, a couple of volts maybe. In a TT system like this, it's quite possible to have 50 volts or more between the neutral and the ground, and that's simply because the distance between the point of supply and the load has some impedance in it, and so the current that flows back, straight currents that flow back to the source of supply through the earth create a voltage that you can see between the neutral wire and the ground at the point of use. So those are two letter designation systems for earth grounding of distribution systems. Hope you enjoyed the screencast, and if you want to get in touch with me, you can reach me at complianceinsight.ca or on my blog machinerysafety101.com. Hope you enjoyed it a lot. Talk to you soon.